The determinants of a matrix can be positive, negative, or even zero. Let's explore what a zero determinant means. Consider a matrix A with elements A, B, C, and D, where the determinant calculated as AD minus BC equals 0. Understanding the meaning of a determinant of 0 is not intuitive. Previously, we discussed a matrix A with values 1, 2, 2, and 1. We can set the determinant of matrix A to 0 by changing a value within A. Let's change the bottom right value from 1 to 4. Now the determinant of this matrix becomes 0. Next, let's plot the vectors from matrix A on a two-dimensional plane. Notice that both vectors 1, 2, and 2, 4 lie on the same line. This means the vectors can span the entire space, indicating they're linearly dependent. Consequently, the rank of the matrix is 1, not 2. This scenario also implies the existence of a vector x such that ax equals 0. All of these observations are interrelated and stem from the fact that the determinant is 0. Now let's interpret the geometric meaning of a determinant of 0. Suppose we multiply matrix A by a vector x and the product is vector y. In this transformation, any vector we multiply ends up on the same line as y. Even vectors initially located outside this line ultimately align with it. Now consider an arbitrary shape or region denoted as S in the plane. Initially, on the original coordinate space, we can measure the area covered by S. However, every point within S eventually maps onto the line, resulting in an area of 0. Once more, the determinant of a matrix represents changes in area. When the determinant is 0, it signifies that every point on the plane transforms onto points along the line. Because every point on the plane transforms onto points along the line, and there are points unreachable by the vectors in the matrix, the determinant of the matrix becomes 0. When the determinant of a matrix is 0, it signifies the presence of linear dependent vectors within the matrix. This reduction in determinants also implies a decrease in the rank of the matrix, alongside the existence of a null space. Essentially, these concepts hold the same idea. Now let's explore the concept of the inverse matrix. The inverse of matrix A is denoted by A with a -1 in superscript. Previously, we learned that the order of matrices in matrix multiplication matters, and the final product can change depending on the order. Suppose we multiplied matrices A and B, and the product is an identity matrix. An identity matrix is a square matrix in which all the elements of the main diagonal are 1s, while all the other elements are 0s. It's usually denoted by the symbol I. Each vector in an identity matrix represents the axis of the original coordinate space. In other words, when multiplying the identity matrix by a vector, the matrix does not alter any coordinates or the space. Let's explore what it means when the product of two matrices A and B results in an identity matrix. As I explained earlier, the products ABX and BAX can differ because in the multiplication ABX, we first alter the coordinates with matrix B, then with matrix A. By multiplying B first and A next, we end up at the same coordinates or coordinate space. In other words, we transform the coordinates twice and the final result remains unchanged. If we multiply matrix A by a certain matrix and obtain an identity matrix as a product, we call the matrix multiplied by matrix A the inverse matrix of A. This means that an inverse matrix of A restores the coordinate space altered by matrix A. We began with a two-dimensional space defined by the axes x and y. Suppose A is a rotation matrix that rotates the space by 90 degrees counterclockwise. Let's visualize the space after it's transformed by matrix A. The inverse matrix of A restores the space back to its original state, where x represents the horizontal axis and y represents the vertical axis. Restoring the original space requires a 90-degree clockwise rotation. Therefore, the inverse matrix of matrix A is a rotation matrix that rotates the space 90 degrees clockwise. For every rotation matrix, there exists an inverse matrix that rotates in the opposite direction by the same angle. Similarly, matrices that shrink the space also have an inverse matrix, as the space can be restored to its original state by scaling the size of its coordinates. However, there are matrices that do not have an inverse. Let's consider the matrix from the previous slide that maps every point on the plane onto a single line. The vectors within the matrix are linearly dependent. After the transformation by the matrix, vectors on the plane will lose their information and be compressed to a single line as two-dimensional data is reduced to one dimension. In other words, this means that different vectors on the plane can be mapped to the same points on the line. For instance, two distinct coordinates A, B, and C, D can be mapped to the same coordinates E and F. This transformation can be expressed as a matrix vector multiplication AX. Matrix A shifts every point on the plane to a line. However, to restore the transformed space back to the original space, we lose track of where the original coordinates EF came from. This loss of information is referred to as information loss. Because of this information loss, we cannot restore the space back to its original space. Consequently, in this case, the inverse of matrix A does not exist. Now, let's explore the condition for the existence of an inverse matrix. This condition is that the determinant of the matrix must not be zero. This implies that every vector in the matrix is linearly independent, making the matrix a full-rank matrix. Earlier, we learned about the relationships between linear independence, the rank of a matrix, and the existence of the null space. Now, we understand the connections between the existence of an inverse matrix and these conditions as well. Let's return to vector operations. Previously, we learned about operations such as addition and scaling. In addition to this, the dot product, or inner product, is another important operation. The inner product is an operation between two vectors that returns a scalar. Suppose we have two vectors A and B. Let's plot them on the plane. We can calculate the similarity of the two vectors using the dot product. Understanding the dot product might not be intuitive, so I will explain it in more detail. Think of it this way. The dot product between two vectors indicates how much they can cooperate or how much they cannot cooperate. Let's replot vectors A and B so that they are perpendicular to each other, with vector A on the x-axis and vector B on the y-axis. This shows that vector A and B have different directions. Imagine two people, one on each of the vectors A and B, moving along their respective vectors. The person on vector A can only see the person on vector B when they cross at the origin where the vectors intersect. Now let's introduce the new vector C onto the plane. Unlike with vector B, the person on vector A can partially see the movement of the person on vector C by observing the shadow of vector C onto vector A. Similarly, the person on vector B can observe the movement along vector C by watching its shadow onto vector B. However, the person on vector B cannot see the movement of the person on vector A at all. When they cannot observe each other's movements through a shadow, the dot product of the two vectors is 0. When they can perfectly observe each other's movement, it's the product of the length of the vectors. Let's define the dot product mathematically. Consider two vectors A and B, with an angle theta between them. The dot product of vectors A and B is obtained by multiplying the length of both vectors and the cosine of theta. This formula allows us to calculate the dot product of two vectors. When the angle theta between the vectors is 90 degrees, they are perpendicular and cosine theta equals 0. Consequently, the dot product also becomes 0. Conversely, when the angle theta between the vectors is 0, cosine theta equals 1, resulting in the dot product being the product of the length of the vectors. Hence, the dot product can be defined using the length of vectors and the angle between them. However, there's another way to define the dot product. Let's consider vectors A and B on a two-dimensional plane. Both vectors A and B have two components. Let A be 2, 1 and B be 1, 2. The dot product of vector A and B equals the sum of the products of their corresponding components, resulting in a value of 4. Now let's delve into significance. As previously mentioned, the dot product of vectors A and B represents the relative movement of B observed from the viewpoint of A. A can perceive the movements along B by drawing a perpendicular line or shadow connecting A to the endpoint of B. Subsequently, A can partially observe the movements along B based on the angle theta. That's why we calculate the dot product by multiplying the length of the vectors and cosine theta. The length of the adjacent side of the right-angled triangle represents the product of the length of vector B and cosine theta. This product represents how much a person on vector A can observe vector B. If the coordinates of vector A are x1, y1, and the coordinates of vector B are x2, y2, then we can define a vector with a direction of this perpendicular line as negative y1 and x1. However, when conducting a dot product, we disregard this perpendicular line and only consider a line parallel to vector A. As mentioned earlier, the dot product of two vectors is calculated by summing the products of their corresponding components. When summing the products of their corresponding elements, the perpendicular components are eliminated, leaving only the parallel components. You can find the length of vector A by taking the square root of the sum of the squares of its elements x1 and y1. Similarly, you can find the length of vector B. If you calculate the product of the length of vector A and B and cosine theta, you will eventually arrive at the same values obtained by summing the products of their corresponding elements. It's crucial to remember the geometric interpretation of the dot product of vectors. We calculate the dot product of two vectors when we want to measure the relative movements between them. Thus, we can use the dot product itself as an index representing the similarity between the vectors. If the angle between the vectors is narrow, we'll get a high value for the dot product. If the two vectors are perpendicular or have a wide angle, then we'll get a low value for the dot product. From the data perspective, when the vectors are far away from each other, it means that they contain different types of information. Since they have different types of information, the similarity index has a low value. That's how we can use the dot product as a similarity index. When two vectors are perpendicular, the dot product of the vectors is 0, implying that they hold different types of information.